Today, we are going to talk about statistics and back analysis in slide 3 and slide 2. My name is Sina Javankhosdel. I'm the product manager of Slide3 software. And today, my colleague and my friend, Brigid Cami, who is the product manager of Slide2, is gonna present with me as well. So I hope you guys enjoy this webinar. This webinar is part 3 of the 3-part Slide3 webinar, and the other 2 parts are available on Rocscience's YouTube channel as well. If you are interested to watch them, you can go to Rocscience's YouTube channel. Today, we're gonna start with a brief introduction to probabilistic analysis in slide 2 and slide 3. Then we will talk about the stochastic response surface method and back analysis using probabilistic analysis. And at the end, we're gonna talk about the spatial variability option. So before we talk about the ways of doing probabilistic analysis, let's look at the reason that we are doing probabilistic analysis. So basically, recently, there were so many different methods of non-circular materialistic analysis, local optimizations have been developed, and also 3D modeling is all new in the industry as well. So the factors of safeties that we are calculating now, they are different from this traditional circular 1.5 factor of safety. And the 1.5 needs to be re-evaluated. Even the standards, they are trying to re-evaluate this number and figuring out what should we do with these lower factors of safety using non-circular search methods. So one of the things that can be done in addition to the factor of safety analysis is defining the probability of failure in models, which is going to help us in the risk assessment and risk management analysis. So in addition to the factor of safety, we have one more parameter, which is the probability of failure. Also, the other thing is, as we all know, the uncertainty in input parameters cannot be properly evaluated with the deterministic single value factor of safety. And again, probability of failure and probabilistic analysis can be great help to consider these uncertainties in input parameters. So these show the value of the probabilistic analysis, and there are other things that we will point out during the presentation. So let's start with a very brief intro to the probabilistic analysis. So the left figure, as you can see, is the deterministic analysis, that you assign one single value to the entire geometry and you calculate factor of safety. In the probabilistic analysis, or a simple probabilistic analysis, which we call it single random variable approach, instead of defining one parameter, we define a distribution for the input parameters, and we sample them in different simulations, and we assign them to the entire slope again. So we don't have one value of factor of safety. We have several different values based on our sampling values from the distribution curve of the input parameters. And at the end, we calculate a parameter called a probability of failure, which is the number of simulations with the factor of safety of less than 1 divided by the total number of simulations. So let's look at these slide 2 or slide 3 dialogues, how we assign these parameters. So basically, we define here cohesion as a random variable, and we define the distribution. We have different distribution types in slide 2 and slide 3. A mean, a standard deviation, which are statistical parameters, and we define 2 other parameters called relative mean and relative max, which basically they show the lower bound and upper bound of our distribution. So lower bound will be mean minus relative mean, and upper bound will be mean plus relative max. After defining this statistical parameter for our input variables, we generate n samples for each property. So basically here we use Latin hypercube with 1000 samples and global minimum analysis type. There are different methods as well that we talk about a few of them today. After defining the sampling method, we start sampling, and based on the parameter that you sample from the distribution curve, we get a factor of safety. And at the end, we get a histogram distribution for the factor of safety, and the green region is the region that all factors of safety are less than 1. We count them, which is 23 points in this case, and divide it by the total number of samples, and it gives us the probability of failure. We don't go through too much of the details. We have, Brigid and I, we have 2 hours of lecture about all these probabilistic methods, spatial variability and stuff. And it's available on Rocscience's YouTube channel. Also, we published over 25 conference and journal papers in this topic, and you can search either of our names, and it will pop up on Google Scholar. So let's look at our first example, which is an open pit mine, and we just want to look at how we set up a model for probabilistic analysis, and look at a couple of results as an introduction. So in the previous webinars, webinar 1 and webinar 2, I talked about how to set up a 3D model, a 3D geometry. So similar to this model that I started from scratch, and you can see the 2D section cuts, how we have the model, how we define the material layers. These are coming from an original volume, and it was cut with a few surfaces, and we created this model. So I talked about it in webinar 1. In this example, I just want to show you how to set up probabilistic analysis. So we go to project settings. The method that I use is Spencer, and we go to the statistics menu, and you can see that the probabilistic option is turned on. So for the sampling methods, we have Monte Carlo, Latin hypercube, and response surface. Basically, Monte Carlo and Latin hypercube, they are very similar, except the way that they sample at different regions of the distribution curve is different a little bit. Latin hypercube is the one that we recommend because it requires less number of simulations. Response surface, Brigid is gonna talk about it extensively, so I'm not gonna talk about it here. We have 3 different analysis type in slide 3 as well: global minimum, overall slope, and multiple minima. Multiple minima is unique to slide 3. So basically, starting from the top, global minimum means that you find the critical deterministic factor of safety and slip surface, keep it, and then when you sample your input parameters, you calculate factor of safety only for that slip surface. And then at the end, you calculate probability of failure. Overall slope means that in every simulation, when you sample from the distribution of input parameters, you calculate slip surface and factor of safety for that specific simulation. So you don't keep the original deterministic one, which is based on the mean value. You calculate in every simulation. Multiple minima is in between. So basically, in the first deterministic analysis, you find, let's say, 800 surfaces. You keep them, and then when you sample in different simulations, for every 800 surfaces, you calculate the factor of safety, which is faster than the overall slope, and the results, depending on the model, can be as accurate as the overall slope option. So for this model, we use overall slope. if we look at the material properties, we have defined 4 different material types. They are all more Coulomb with different values of cohesion and friction angle. And you can either go to the statistic menu from here, or you can go close this one, go to statistics, material statistics, and look at the parameters, statistical parameters that we define for each material. So for all of them, we define cohesion and friction angle as our random variables, and the distribution is log normal. The recommended value for the coefficient of variation for cohesion is up to 0.5, and for friction angle is up to 0.2, which is roughly the same values that we use for this example. Let's go and look at the results. So we go to the results tab. Factor of safety using a Spencer method is 1.26, and probability of failure is about 34%. So this is the critical slip surface, deterministic slip surface. We have an option to show all surfaces. If you do a deterministic analysis, show all surfaces means all deterministic surfaces that we search to find the critical slip surface. But when you do probabilistic analysis, show all surfaces, especially for overall slope option, is all the slip surfaces that we found for every simulation in the probabilistic analysis. So all 3,000 simulations, you can see that this is the deterministic, and these are the sample number and the failure surface for that sample. So you can see that why we recommend to do overall slope analysis, because if you do a global minimum, you just keep this one, the most critical. But when you do overall slope, the minimums that the software found in each simulation, they are very different. So at different locations, different regions. And an interesting point, looking at the surfaces, you can probably say it here that we talked about something, a new option in slide 3 and slide 2 called multiple modal optimization, MMO, which in the deterministic analysis, it gives you a couple of minimum factor of safety surfaces. There is another way of doing it, which is to do probabilistic analysis to find different failure regions. And you can see that on the other side of the open pit, we have a concentration of the critical surfaces found in the probabilistic analysis. So basically, if we do MMO on this model, we should get these two regions as two critical regions of the factor of safety. Okay, let's turn these all surfaces off, and let's look at a couple of statistical results. If you have any questions, please feel free to type down in the question section, and we would be happy to answer your question. We will answer your questions live, and also at the end, we have some time to talk about a couple of them. So in terms of statistical results, we can plot different histogram, scatter plots. Let's start with the histogram. So you can plot the histogram of the factor of safety, and you can also highlight it. For example, for this case, we want to highlight it for the region of the factor of safety of less than 1. So we click on plot, and the software gives you the histogram. And the green columns, these are for the cases that we had factor of safety of less than 1. The software gives you the number around 1,000. And also it gives you the mean of this distribution, standard deviation, probability of failure, reliability index, and also it finds the best fit for the distribution of the factor of safety. So a lot of interesting information. You can always export it to Excel as well. You can look at different scatter plots as well. So basically, let's plot factor of safety versus cohesion of the material number 2. So again, green points are the points, cohesion values that the factor of safety has the value of less than 1. The software gives you, when you have a scatter plot, this line as well. This is the corresponding to the correlation line for between the cohesion and factor of safety. And the software gives you the correlation coefficient as well. So it's 0.13, about 0.13. So basically, factor of safety and cohesion of material 2, they have the correlation coefficient of 0.13. Now, if we do the same thing and we plot factor of safety versus friction angle of material 2, you can see this scatter plot and the correlation coefficient of 0.64. It's very interesting because you always want to know in your design which parameter is more effective on the factor of safety. And doing probabilistic analysis like this and looking at this scatter plot, it obviously shows that for material 2, factor of safety is much more affected by the friction angle compared to cohesion. So you can do it for other materials as well and see this correlation between the factor of safety and the parameters. So that's another interesting output as well. So this was some 3D probabilistic analysis for this example. Now, if I want to show you something in 2D as well for the same model. So basically, I took 3 2D sections at 3 different locations of my model. And to look at the same type of analysis, first of all, if I open the Slide2 file, so basically, these are 3 2D sections that I had on my 3D model. As I mentioned there in the previous webinars, there is a more than 90% integration between Slide2 and Slide3 now in our release last update of the software. So basically, if you go to the statistical options, they are the same. If you go to the material statistics, they are exactly the same as defined in Slide 3. If you look at the results, that's quite interesting. So basically, we get, for 3 different sections, we get 3 different factors of safety and a huge difference between the probability of failure. So really, in the previous webinar, I talked about the 2D, 3D results comparison. It really depends on where you take the 2D section, and factor of safety changes from 1.1 to 1.7. And probability, now that you have one more parameter to compare between 2D and 3D, you can see that probability of failure changes from 55% to 0.9%. So which one of these 2D sections they are representing the 3D model? So that shows the advantage of doing 3D modeling for more complicated models like this to get a proper factor of safety and now a proper probability of failure. So let's move on. I'm going to pass the presentation to Brigid. She's going to talk about stochastic response surface method.
Thank you, Sina. Hello, everyone. So now we'll go over stochastic response surface. So first of all, where does this fit into the probabilistic flow? So this is the flow Sina reviewed in the beginning. You start by defining your distributions, you generate samples from each of those distributions, and you calculate the factor of safety for each simulation to get the probability of failure. Now, obviously, the most time-consuming step here is calculating the factor of safety for every single simulation. And the point of response surface is to help with this. So what exactly is it? It's a method that uses machine learning to train a model that predicts a factor of safety for each of those simulations. And the way it does that is, say the user wants 5,000 samples for their analysis. It computes a smaller number of samples and it uses those to train a response surface model. Then that model is what predicts a factor of safety for all 5,000 simulations. Okay, so how do you set this up in Slide 3? So as Sina showed, this would be in project settings statistics. You would just pick your sampling method to be a response surface. Then you enter however many samples you want, and the program itself will determine how many it needs to compute. And before going into the live examples, I just want to show some simple cases, not simple cases, but non-live examples to explain how effective response surface is. So this first one is with slide 2. There's a yellow material with a weak layer and a load. There are 3 random variables defined. 2 are material properties, 1 for the soil, 1 for the weak layer, and 1 is for the load itself. So the load is also variable. So we ran that model once with Latin hypercube, once with response surface, and then we compared the first 100 simulations. So the factor of safety that response surface predicted versus the one that Latin hypercube actually calculated. So Latin hypercube is in orange and response surface is in green. And you can see that it's actually quite impressively accurate at predicting. It's almost exactly the same for all samples. Some of the more edge cases that go further are slightly off, but still they're very much in agreement. And if we look at the probability of failure results for that example, the first row is Latin hypercube, the second row is response surface. So if you do Latin hypercube with 1,000 samples, you get a probability of failure of 73%. If you do response surface with 1,000 samples, you get the same probability of failure, 73%. But like we said, this actually ends up computing 40 samples to train the model. So then the important column is the computation time. Latin hypercube takes about 7 minutes, while response surface takes about 20 seconds, which means it takes 4% of the time. So this is all fine. We saved 6.5 minutes. But in slide 3, this actually has a huge impact. So this is the model that Sina went over, our live example 1. The same random variables that she talked about. We computed this with Latin hypercube and with response surface. And the results are at the bottom here. So probability of failure with Latin hypercube was 34%. With response surface, it was about 30.5%. But the real difference is the computation time. So with Latin hypercube, this model takes 62 hours, whereas with response surface, it takes 4 hours. And I think it was 3,000 simulations. And if you look at the pictures, the one on the left is Latin hypercube, the one on the right is response surface. So because response surface, of course, computed less samples, there are less surfaces here. So these are the surfaces that Sina showed, the global minimums from each simulation. So even though there are less surfaces, it still gets the minimum regions. And that's why it can predict so well. Okay, so this is great, saves a lot of time, similar results, but don't forget that this is a predicting function. So although we've done hundreds of verification examples here that have proven that response surface agrees very well with Latin hypercube, still it is predicting. So we always recommend that you use response surface to set up your model. For example, see what impact does support have on probability of failure and so on. So do that to get your model all set up. And then at the very end, run Latin hypercube overall slope overnight for peace of mind. Okay, so now we'll look at an example with response surface. Open it up. So this model has featured in the last 2 webinars. It's the levee with the retaining wall. So I will zoom in here. So this is the levee and this purple one is the retaining wall. And there's also a water table here. And as discussed in previous webinars, a lot of pore pressure was being generated in this region. So to relieve that, we defined relief wells. And the way we did that was by running this model in RS3, running a seepage analysis. And RS3 is our 3D finite element program. and then getting the pore pressures and importing them into slide 3. And we can see them here. So these are the pore pressure contours. So before we look at the spacing of the wells and such, let's look at how response surface was set up. So we go to project settings, statistics, and we see that response surface is selected with 5,000 samples and overall slope. Now, to reiterate, there are 5,000 samples here, so we're going to get 5,000 factors of safety, but a smaller number of samples will actually be computed to train the model, which I'll show in a second. And let's also look at the statistics that are defined. So 3 of our materials have random variability for a total of 6 random variables. Okay, so now I'm just going to start computing this model. I defined this with a very coarse, simple search, just for the sake of showing what I'm about to show now. So this is the global search, the deterministic. And then this is the probability progress. So you see that even though we defined 5,000 samples, it's 168 that are actually computed to train the model. Now I will abort this because we will not wait for this. I have computed the model with a much more robust search, cuckoo and optimization. And now we'll just have a look at the results. So this case has the relief wells spaced at 50 feet in the y direction, so this way. And if we look at the results, we see a deterministic factor of safety of 1.4 and a probability of failure of 2.7%. Now, one of the points that was discussed in the last webinar is the fact that this isn't the sort of model you can do in 2D. And the reason is because it has 3-dimensional boundary conditions. And what that means is if you model this in 2D, you can't account for the spacing of the relief wells. You're basically assuming they are continuous and they go infinitely into the page. So doing it in 3D gives us a chance to see how much of an impact the spacing has. So this one is 50 feet, and the probability of failure is 2.7%. We also ran it with 200 feet spacing, and you can see the probability of failure increased a lot to almost 16%. And the deterministic factor of safety went down to 1.2. If you do this only in 2D, the deterministic factor of safety was something like 1.7. Okay, and then just to drive the point home, we look at a scatter plot of anything that includes factor of safety. We can see that we have 5,000, presumably here, factor of safety points. So all of the predicted values. Okay, now we will return to the presentation. So next we'll talk about back analysis using probabilistic analysis. So probably everyone knows what that is. If you have a slope that already failed, you know the surface, and you want to figure out what the material properties were based on what you know about the failure. So this can be done with a probabilistic analysis in Slide 3. And for this, we'll just dive straight into the example. This model is a road with a slope next to it. So you can see the load represents the road. And since this is a back analysis, we already know the shape of the failure surface. So the first thing we would do for the back analysis is import that. So we'll do import geometry, and this is our surface. Now select it. So that's the actual failure. The next thing you would do is you want to define this as the slip surface. So I'm going to go to surfaces, add user defined slip surface general, and it will automatically select the only one that's defined. And I click OK. And the other thing you want to make sure is that in surfaces, slip surface options, you've selected user-defined surface. This ensures that this is the only surface we're computing. And then we want to set up statistics. So this one we're going to run with global minimum. So same thing, we already have the surface. We don't need to search other options. So global minimum. And global minimum is actually super fast, so there's no need to use response surface ever if you're using global minimum. So Latin hypercube 2000 samples. And then we'll look at our material statistics. So because this is back analysis, we define everything with a uniform distribution, meaning we consider everything equally. So cohesion in this case is uniform with a mean 70 plus minus 30. So from 30 to 100. And similarly, friction angle is uniform 35 plus minus 15. And we can compute this. And look at the results. And we don't really care about these. We just want to see what combinations of cohesion and friction angle lead to the factor of safety 1 case. So we'll go to statistics scatter plot. And we're going to plot cohesion versus friction angle. And we're going to highlight a range between 0.99 and 1.01. Now, you may want to consider a wider range, but for the sake of this example, this is okay. Plot. And the green dots, so this line, represent the combinations of cohesion and friction angle that give us a factor of safety of 1. So we can hover over them, for example, cohesion 54, friction angle 25, give factor of safety of 1, and so on. Okay, then I defined a 2D section here and exported it to slide 2. So I'll open that. So you can see this is our slip surface, which we input in slide 3. Everything was exported as we defined it, including the statistics. Yeah, we'll just compute this. And we can look at the same thing here. We can go statistics scatterplot, cohesion friction angle, and I've already set this up, the range roughly 1. And again, we see this line that leads to factor of safety equals 1. And forgot to mention in slide 2 to do user defined, you would set non-circular block search with 1 surface, and this was also done automatically when exporting from slide 3. Okay, so we've done that now. Now you may be wondering what's the difference between probabilistic analysis and sensitivity analysis in slide 2 specifically. So I will just show that with a quick example. So I'm adding a scenario, calling it sensitivity. And in this scenario, I'll go to project settings, statistics, turn off probabilistic, and turn on sensitivity. Notice that all these options are gone. And that's because sensitivity uses just a default 50 samples and global minimum, which I will demonstrate. And if you go to statistics materials now, you can also notice that for sensitivity, your distribution option is gone because it has to be uniform. Okay, and now I will compute this one. Okay, and now the only statistics plot available to us is the sensitivity plot. So I'm going to plot the factor of safety for both of them. And this, of course, looks very different from our scatter plot from before. And the reason is that sensitivity analysis only varies 1 variable at a time. So for example, this blue line is cohesion. And when it's trying all these different cohesions, everything else is fixed, including friction angle. So then we would just go here to factor of safety 1 and see what the cohesion is. And similarly with friction angle, everything is fixed and only friction angle is varying. So that's the difference between sensitivity analysis and probabilistic analysis in slide 2 anyway. Okay, and now I will pass it back to Sina to continue with spatial variability.
Okay, thanks, Brigid. There were a couple of questions. I think we'll spend some time at the end to answer these questions. Okay, so let's talk about the spatial variability. Basically, what we have talked so far is a single random variable approach, which does not consider the spatial variability of the parameters. So this option is available in slide 2. So in the project setting, the statistics, you can see that this is a spatial variability analysis. You can turn it on, and it only works for the overall slope analysis because it doesn't mean anything to do global minimum deterministic when your material properties are changing in each simulation. So we define one parameter, which is a spatial correlation length in the statistical material menu. What is this spatial correlation length? Basically, what a spatial variability means is that in different locations in your soil profile, you have a different property. But when you do sampling, how do you want to assign the property from the sampling at different location? Are we going to change the property in every location, every point? Or there is a rule or there is a parameter? This is where we talk about the concept of a spatial correlation length, which is defined as the length that the soil properties are the same. In other words, if you have two boreholes taken from adjacent locations in the soil profile, they tend to have very similar values. And the range that they have similar values, we call it a spatial correlation. So to define it, like different things that we have talked about so far. So this is deterministic analysis. Let's say we define a cohesion parameter with a mean value of 2 kPa and a standard deviation of 0.5. So in the deterministic analysis, we assign 2 kPa for the entire profile. In the probabilistic analysis, a single random variable approach, which basically means that the spatial correlation length is infinity. In each sample, we assign different properties. We pick different properties from the distribution curve, but we assign it to the entire geometry again. So we don't change them from one location to another one. But when you have a spatial variability, let's say you define the spatial correlation length of 1 meter. So at one point, you pick a value of cohesion of 0.5 kPa. And one point, if the distance between the second point and the first one is greater than 1 meter, which is the spatial correlation length, they tend to have very different values. In this range of mean 2 kPa and a standard deviation of 0.5, it's a big difference between 0.5 and 2. Let's try a larger spatial correlation length. In this case, if we pick two values, and if their distance is greater than 20 meters, the values might be very different. So, and this is isotropic spatial correlation length. It means that horizontal and vertical, they have the same value. So basically for this value of theta equal to 20, we can expect 20 by 20 regions because horizontal and vertical correlation lengths are equal. So you can see that even for the orange and yellow ones, they are 20 by 20. So this is the range of correlation lengths that we tend to have similar values. So what's going to happen to our process is we just define the spatial correlation lengths. And when we create n samples, now we are generating n fields because each field is spatially variable. And we pick one value from the distribution curve of our input parameters. We consider the spatial correlation length, and we create different fields in different simulations. Now, for each field, we calculate factor of safety using limit equilibrium method, and we call it random limit equilibrium method or RLEM. It's interesting that we released a spatial option with the surface altering optimization and Slide2 software at the same time. And without combining a spatial variability with non-circular materialistic search methods and surface altering optimization, you are not able to get correct results because, as you can see in this model, we have weak regions, strong regions. If you use, for example, circular search methods, circular is a circle. It doesn't really care if it goes through the weak region or a strong region. It tries, but it has to be a circle. But with a flexible search method like metaheuristic search methods and local optimizations, now you can see this failure surface following the weakest failure path in your profile. And to emphasize on the fact that this is a still limit equilibrium and method of slices, you can see the slices that we define. One more step that we added to a spatial variability option to slide 2 is to do subsampling, because each slice might go through more than one box with different material properties. So we do subsample on the base of each slice to make sure that we cover all the properties defined at the base. Okay, let's look at our last example, which is a bonus example for a spatial option. Let's see what we have here. So this is a Sugar Creek embankment example. Basically, in the deterministic analysis, we compare the results with the results of literature. So we use non-circular search methods and we got the factor of safety of 1.59, and we did the shear strength reduction method in RS2 software, and we got the factor of safety of 1.6. So they are equivalent at the same failure surface. And this highly weathered shale, the orange region, is the weak material that we have. Now, let's go to our probabilistic model and see what we got. So this is our model. We have something called property viewer in slide 2. So basically, we define the correlation lengths of 40 meters in horizontal and vertical for 5 layers that we have here. For cohesion, we only have 2 layers that they are variable. For friction angle, we have all the layers. You can look at the grid option. You can look at the normalized option. The reason that we have normalized option because each layer might have different mean values. So to show better the variability of the parameters along each layer, we normalize them with their mean value. So this is one of the fields, and we have like 50,000 fields for this example, 50,000 simulations. And if you want to look at the results, this is the results of the probabilistic analysis. We have the factor of safety of 1.40, 59, 1.6 almost, and probability of failure of 0.59%. Again, you can look at the property viewer, and for this one, you can look at different failure surfaces for different simulations. And you can look at most of them. That first of all, this layer, most of the time it is blue because it's a weak layer. And also the failure surface is following this layer, which is a blue region, which shows the advantage of using these complicated methods. Just look at this shape of this failure surface, and you see how the software plays with these surfaces to make sure that they are going through the blue regions. Now, the question here is, what if, because this option is only available in slide 2. So sometimes you don't have to do 50,000 simulations. For practical purposes, your field is kind of known, and you know how parameters change in your field, where are the weak regions, where are the strong regions, and you don't need to do 50,000 random generations of the field. So for that, let's say, let's go back to our modeler. Let's say my field is like field number 4. So I want to know what happens to my factor of safety only for this field, but not just with a slide, not just with 2D limit equilibrium method. What about finite element method? What about 3D analysis? So we added an option to slide 2 that you can export samples as discrete functions. So basically, for each layer, you can export the spatial field as a discrete function. Discrete function means that you have x, y value and c and phi. So you can define it at different locations. This is a material option in slide 2. I'll show you in a few minutes. So basically, that's what I did. And I exported the discrete functions for different materials. So these are all 5 layers for sample number 4. And I started with the slide model. So you don't need to do probabilistic analysis. You just go to properties, define material, and define discrete function, go to edit. And these are coming from our spatial field for field number 4. And if you look at the property viewer, it's equivalent to what we had in the spatial option. So we did the analysis for this one, and we found the factor of safety, which is 1.33. So for that specific field, factor of safety of 1.33. We did the same thing in our RS2 software. So basically, you can just drag and drop a slide into RS2, and it's gonna take all the properties from a slide to RS2. You can see that these are all the layers that we have as discrete function. And in RS2, we have a property viewer as well, so the same as the slide. And if you look at the results of RS2, factor of safety is 1.35, very similar to a slide. So you have also the option to copy the critical steep surface in RS2 and in a slide and bring it to RS2, which we did. And you can see that the failure surface matches perfectly between two software. So the results are matching, the failure surfaces are matching. Now, what if I want to look at the 3D results of the same model? We can extrude it, it's fine, but this is a spatially variable. So I just take this model, drag and drop the 2D model into slide 3, hit OK. It's gonna give me a suggestion for the extrusion depths. I'm gonna keep it. And yeah, so this is the field that we brought from slide 2, and you can see that this is defined as a discrete function. And yeah, it's changing spatially in my model. If we go to the material, define material, you can see that this is the discrete function defined and for different layers. And here is the results. Let me turn off the discrete functions. So this is the critical steep surface which goes through the weak layer, and it's very similar to the 2D model. Factor of safety is 1.54, higher than 2D for sure. And now, sometimes when you have these kind of weak layers, there is a way of pushing the failure surface to go through the weak layer even more. So to do that, because this is a discrete function, what I can do, I can just use the weak layer option in a slide 3 software. So I'm gonna hide these layers, including the weak layer. I'm gonna select the surface below the weak layer and use this option as weak layer surface. So the software is gonna define this layer as a weak layer. I'll go with material 6 because I wanna define a new material for the weak layer. And for material 6, I will use the properties that I had in the original model as the mean parameters for this layer. So basically, when you do a probabilistic analysis, you still have these mean values. So 33.2 and 12.8. Cohesion was 33.2 and friction angle 12.8. So And this is gonna be my weak layer. I ran this version as well in advance, and the results are slightly better because the software pushed the critical slip surface to touch the weak layer, and weak layer is defined with the mean values of the original parameter of this layer, and the factor of safety is slightly lower, which is 1.49. So this is showing how you can, first of all, add a spatial variability for specific fields and run it in a Slide3, and also how you define the weak layer to push the failure surface to go through that layer. So this is the model. This is one of the examples of the 2D failure surfaces. And here is a little bit, we started with talking about practical application and stuff. So for this model, deterministic factor of safety is 1.59. If we use a single random variable approach, we get the probability of failure of 3% versus 0.2% with and without cross correlation between parameters. If we consider spatial variability, without cross correlation, we get a probability of failure of 0.6%. And with cross correlation and spatial variability, we get probability of failure of 0.01%. This value actually is the value for design purposes, which shows that if you have a model, you should consider the spatial variability and cross correlation between the input parameters. This concludes our webinar today, our part of the presentation. We get to the questions shortly. We have about 5 minutes. Brigid and I, we decided to have a webinar on August 3rd about what's new in Slide2 and Slide3, because we have developed several features recently to these two software, and also until August. One of them in Slide3 is this texture mapping and train generator. We have export generalized anisotropic from Slide3 to Slide2 and other options. So we will talk about them on August 3rd. Rocscience will announce the webinar on social media and on Rock News as well. So let's go through the questions. Brigid is here as well, so we can answer a couple of them.
Okay, one of the questions is, what's the logic or reason behind defining the material properties with uniform distribution with back analysis?
Basically, for the back analysis, because we want to look at the range and if you define a normal distribution, for example, each value of the distribution has its own frequency, which can be higher or lower. But when you do the back analysis, you just want to give all of them the same frequency, the same value. So, and we just want to see how your factor of safety changes based on changing the input parameters. That's why you define uniform.
Okay, one of our other questions is, can back analysis be carried out in Slide2? Yes, you do it exactly in the same way. Like the options are identical. You can also consider cross correlation. Have you published any papers to show that spatial variability in Slide2 matches published results from the random finite element method?
Yes, we have done a lot of them actually. I think, as I mentioned, if you look at our Google Scholar, because the first thing that this method, random limit equilibrium, the original method was random finite element method, which combines the random field and finite element method of analysis. So the first thing that we did was to confirm that this limit equilibrium is giving the same answer. And I showed you in one simulation that matched finite element results matches limit equilibrium. It's a very big discussion about this matching things. But for the applications that we have seen the papers, we first compared, and also we always match the results with finite element, at least for one simulation. And in terms of the curves and probability of failure versus factor of safety, yes, we did a lot of comparison with finite element. A lot of questions. What is there was one question, what is the typical values for a standard deviation? We have a couple of tables in Slide2 that talks about the typical values for the coefficient of variation of soil parameters. So you can reference to those parameters. These are typical values. What is the other question is, what is the most appropriate distribution type? That's a very good question. So basically, in terms of experience that we have, if you have data and you can fit any distribution to your data, you can define them in the software. So if you have the data, if you don't, we recommend to go with log normal because soil properties are positive values. So a log normal distribution always gives positive values. So it's better to go with log normal.
Oh, and maybe we have time for last one here. For the road back analysis example, how do the 3D back analyze strengths compared to the ones from 2D? Actually, they were almost identical because the model is extruded. Slide 3 is a little bit higher because of the 3D effects, as with all extruded models.
Yeah, I think because most of the times 3D, if you are comparing like more complicated models, 3D gives higher factor of safety. So in the 3D model, probably the change of the parameters to reach to the factor of safety of 1 is less compared to 2D, that you need to increase your parameter more to reach the factor of safety of 1. Okay, that's all. If you have any further questions, please feel free to contact us and we would be happy to answer your questions. And thanks for attending this webinar. Enjoy the rest of the day or night, wherever you are.